So, good afternoon, everyone. On behalf of ETIP SNET, Zabala, Anastasiya, who helps me, my co-chairs, working group 2 members, I am very pleased to welcome you on this ETIP SNET seminar on storage. We have had several requests in order to organize such a seminar on storage, so we have decided as a first round, let's say, to begin with an hour-and-a-half seminar on storage, technology, markets, and economics. And I'm sure you will have some interesting information during this presentation this afternoon. It will also be the occasion to introduce the new ETIP battery, which was born last year, which focuses on one technology of storage, I mean batteries. Luigi Lanuzza, who chairs the working group on stationary application, will be the first speaker. And he will introduce what ETIP battery is particularly doing. I just would like to give you some quick information on ETIP SNET for those who don't know, and its working group 2. ETIP SNET is one of the 10 European technology and innovation platforms, among others on wind, photovoltaics, for instance, and of course, battery, as I've just mentioned before. ETIP SNET is a system integration ETIP focused on smart network for energy transition. ETIP SNET has several objectives in order to help the European Commission to prepare the future energy transition, and for this has been working on 3 documents, and as you can see on the pyramid. The first step was the 2050 vision, with a particular focus on low carbon energy system integration. Then a 10-year roadmap in 2019 and an implementation plan in 2020. ETIP SNET has 5 working groups, one on smart grids, one on storage and sector coupling, one on flexible generation, one on digitalization, and one on innovation. And I have the privilege to chair the second one, which is holding this seminar. Working Group 2 addresses technological and market developments related to energy storage solutions, and also the interfaces between energy sectors, which with the aim to ensure enough flexibility to the system. The group covers all energy storage technologies, as you can see in this list, and also covers the entire value chain. I mean, development of the technology, integration, impact and flexibility, and cost analysis. Interfaces between the power sector and the heat sector, the gas sector, and the transport sector are also included. To finish, here are some some other elements on the working group. We are currently 45 members, and I would just like to say, feel free to join us to participate to this storage adventure. And I wanted to make this introduction quite short to let to have more places for the technical presentation. So, one more time, be welcome on this seminar, and we'll leave the ground to Luigi for his presentation on ETIP battery. So have a nice afternoon, and please, if you have questions, just write them on the chat, and we will relay them to the presenters. Thank you, and have a good seminar. So here we go for Luigi.
Hi, Luigi. Are you with us?
Luigi, are you here? He was there just before.
He is online. I'm not sure why he's not answering.
Do I have to do something to close my screen?
Your screen isn't being shared right now.
Okay. Luigi says, can you hear me in the chat?
No, he must have some technical problems.
So in order to keep the time, can we skip the two first presentation in order to
All right, maybe
try to solve the technical problems during the
Yeah.
first presentation?
Okay, so our next speaker is Mark.
Is Enrique going to be presenting before me or after? Can I share my screen?
I think it's best if you go first. Normally you should be able to share your screen.
Perfect.
Okay, my name is Mark Howitt from Storelectric Limited. I'm going to be presenting twice on this presentation. The second time will be when I present Storelectric. So this first presentation is a very neutral presentation going through the various challenges of converting intermittent generation to variable and baseload in quite low-level detail. So the first need of storage, of converting intermittency into dispatchable energy is energy balancing. The challenge is that most renewable generation is intermittent, and we're moving towards renewables and away from dispatchable power stations. Dispatchable means available on demand. We want our hot drinks when we want our hot drinks. We're not going to wait for when the wind's blowing or the sun's shining before we decide to have our hot drinks. So therefore, we need to be able to store electricity from when it is produced to when we want to use it. Because apart from that, the light in your room is powered by electricity that's generated within the last 2 seconds. So therefore, then there needs to be storage to be able to balance it. But what about interconnectors as a potential means of doing so? Well, right now, these countries in red are depending on imports during times of system stress. Now, times of system stress are defined as those with low renewable generation and or high demand. So basically, when the sun's not shining after sunset in the evening, if the wind's not blowing and you're in peak demand time, that's a time of system stress. And all these countries are importing today in those times. By 2030, they'll be importing. By 2040, they will be importing. By 2040, they will have just enough energy for their own electricity systems. This is according to each country's own energy transition plan. Now, you can believe that if you want to, but I frankly don't believe that France, for example, is going to have 40 gigawatts of nuclear build out on time and to cost by 2040. I look at Flamanville and think that that's a bit aspirational. So that is the situation. Essentially, on today's plans, only 3 countries, Iceland, Norway, and Switzerland, are going to have surplus to export. And that's not going to be able to power the rest of the continent during times of system stress. Every single country's exports will be killed apart from those 3, because these times of system stress are largely concurrent. So therefore, there is a big need to store lots of electricity from when it is generated to when it is needed. The second need is on distributed systems, because an awful lot of the renewable generation is being put onto the distribution network, not the transmission network. Think of the solar panels on your roof or the odd turbine or two on an agricultural farm. This is a forecast that was put out by National Grid in the United Kingdom, seeing how the demand on the transmission grid is going to change over time. The top line is 2015, which is the year in which they put out this forecast. And the bottom line, they said, in the worst case scenario, because there's going to be so much generation on the distribution grid, there's going to be below 5 gigawatts of energy going around the transmission grid. Now you need 5 gigawatts in the UK to be able to provide sufficient power to power the starter motors of all the power stations. So essentially, if you go below 5 gigawatts, you're in a black start situation. Now, unfortunately, they underestimated the amount of solar on the grid at the time, and they also didn't consider what happens if the wind's blowing at the same time. So the first time they came across the worst case 2035 scenario was actually the same year in August 2015, for which reason they've never put out this curve since. So there is a big issue that we need to keep a certain amount of electricity flowing through transmission grids, even when it's not needed to be sucked into distribution grids because they've got enough of their own generation. And that's where storage can play a large role in taking surplus electricity. This is happening increasingly so. And as we can see from the lockdown, this is the demand curve that has actually happened last month on the 3rd of May. Because demand was so low, and at that time the weather was absolutely perfect for renewable generation. It was not only beautifully sunny in Britain, but also nicely breezy as well. So there was an afternoon peak, an afternoon trough of demand on the transmission grid that was below the overnight trough, because so much, the yellow portion, was being produced on the distribution grid. And so during the whole period, they've been spending somewhere between 10 and 30 million pounds a day, so 12 to 36 million euros per day, per day, in turning down nuclear and wind, turning imports into exports on the interconnectors, purely in order to be able to pay money to turn up the power stations. And why is that? That is because of lack of inertia, which is the next subject. Grid stability. What do you need inertia for? If you think of yourself as it being in a car, if the car engine fails, inertia means that you can drift to a halt. If you did not have that momentum, in cars, you call it momentum because it's all in a straight line. If you did not have that momentum in the car, it would feel like that when you get an engine failure. With power stations, they are large rotating machines, and they have inertia, but this is rotating inertia. That means that if they get a failure in the system, the equipment is still rotating and will continue to generate electricity for the milliseconds and the seconds required to slow down the change in the grid. And when I say that they are large rotating machines, they are very large rotating machines. There is a man in that picture if you have a microscope. And too little inertia means an unstable grid. It was this lack of real inertia that caused blackouts for 1 million people in the United Kingdom last August. How much inertia are we going to have? Well, these are the forecast curves. The units are unimportant. Everyone measures inertia differently. But in 2009, we had the top line. 2020, we've got the middle line. And by 2029, we'll have the bottom line. you can see the amount of inertia is plummeting. And as inertia corresponds directly with system stability, you can see that all the grids are scratching their heads to wonder how they can deliver system stability. And that's the result in Britain last August the 9th of not having real inertia. They had lots of synthetic inertia from batteries, but because batteries have to be triggered, that gives a response time. Because of the response time, whether it's milliseconds or seconds, the rate of change of frequency is still very, very high. The delay between the failure and the response time is a spike in the electricity system, and that's what caused the problem. So only real inertia can prevent it happening. On the other hand, synthetic inertia was very good for helping it to recover from the problem. The other thing that inertial plants can give is real reactive power and load. So if you think of active power is what we use to power our equipment, but reactive power is what gives it the push to go around the system. You can think of it that way. And if you don't have enough reactive power, or if you have too much of it, it can be a problem. And therefore, rotating systems can put more on or take more off at will. Systems with inertia are anything with large rotating machines, which is power stations, hydro and pumped hydroelectric, compressed air energy storage, liquid air energy storage, and flywheels. We're going to be hearing about our compressed air energy storage and other people's flywheels, and also liquid air energy storage later on in this seminar. Without inertia, wind generation, solar generation, interconnectors have no inertia because they're DC connected, and batteries, anything that is connected with a DC link somewhere in the system has no inertia, no real inertia, and they can only provide simulated inertia. Then there are black start issues. What happens when the lights do go out? You need to be able to do a black start, starting a facility without external power. That creates a frequency reference, which enables it, if it's got surplus energy to spare, to start the neighboring generation and create what they call a power island. And you need to deliver all of that. You need power, you need inertia, real inertia, because every time you start up a neighboring plant, it's going to give a hit back onto your own plant. You need to keep the frequency monitored, and you need the duration to be able to keep it up and running long enough to get these other plants started and stabilized. And then the various power islands that are started up are then synchronized with each other. So, in conclusion, the question is, which is the willing technology? And frankly, every single technology needs something, has its place in the system. You can see here, I've put a correlation between response times, durations, and size for the various different technologies. And you can see that they all have different profiles, which is why they can all have something to contribute to the system. The problem we've got at the moment is that people are expecting certain technologies to do everything, especially batteries. They think the batteries are the answer to all prayers, but they're not suitable for every single technology. They can't deliver real inertia. They can't deliver long durations cost effectively or immense scales. So therefore, we need a really good mix with all of these technologies, and all together enable renewables to power the grid. The way I conceive of this is very, very simple. Think of a map. You need enabling renewables to power the grid is rather like the road system enabling the economy. If we only had motorways and main roads, then we couldn't get to our homes, offices, and shops. If we only have small roads, we couldn't get anywhere fast or far. If we try and go far on small roads, it'll take forever to get there. If we try and go fast on small roads, we'll crash. Essentially, we need to use each technology for its own strengths and not to try to apply one solution to all problems. Thank you very much.
Thank you, Mark. Enrique, you take the lead.
There I go. Can you hear me?
Perfect.
Yeah.
Okay. And am I sharing my screen already, or?
Perfect.
Yeah, we can see it.
Okay, there I go. So thank you, Mark, for the introduction. From the technology perspective, as you saw, well, every technology, storage technology, has its role in the energy system, and I will give you a brief overview of how the energy storage market is evolving in the past years, and how would be in the future. I will be brief. Just I will take 5 minutes of your time, but I will give you some highlights that may be of interest, and we can afterwards develop them more if necessary. So how is the market ongoing, and what is the forecast for the following years? So almost all reports ensure a market increase in energy storage applications, about 15 to 20% increase in the annual growth rate. If we divide in terms of application, we can see that mainly mobility is increasing a lot. Of course, electronic devices, which is a demand that has been high in the past and will continue growing with all the IoT and etc. developments, and a new that is coming, which is stationary storage as a new part that will pop up effectively and heavily in the market in the following years, mainly in China, but also Europe and North America appear as the markets with more perspective in the following years. So if you see here, mainly in this part, I don't know if you see my pointer, but mainly in the following years, the increase is very high, and most of the market forecast reports that you can see in the arena points to the same direction. So we have brilliant future perspectives, and it's an important market that we're facing, and interesting and thrilling as it's all in the energy system. A part that I always check when I divide or when I check on a market is how technology is developed in terms of patent applications and also articles publication. So if we see, I just took out one example on the batteries electrochemical storage as one of the energy storage applications we have. But of course there are many, but the graphs are similar as we go across them. Is how they're increasing in the recent years, and the trend line is crystal clear. So we are increasing a lot in terms of applications, both cumulative and also every year. So that shows that there is a market interest in terms of technology, and this opens a huge window on future development, and of course in market share. The drawback is that the main countries where we see patents applications, of course there are different markets for patenting, and USA is different, as you know, from other countries, mainly the rest of them. But Japan, USA, Korea, Germany, France, China are leading this development. And as you see, there is a very important gap about what we are doing at European level and also at international level. So Japan is highly above us, and also USA. So the east part of the world is investing a lot. This is not any news. You all know them, and because of that, mainly Europe is doing a high effort, or planning to do a high effort also in investment and research and development in the area of energy storage. But there is a lot to do because we are a little bit behind about our colleagues in Asia and also in the United States. So if we go to the European market, the energy storage market contracted in 2019 1 gigawatt hour with a cumulative installed capacity of 3.4 gigawatt hour across all these segments in energy storage, excluded pumped hydro, which is not in the graph that I'm showing on the right side of the slide. So as you see, the amount of storage that is being installed and contracted at the European level is increasing year by year. We have the report I'm showing is from ESSIP, the European Association for Storage of Energy. You can download a small free part from the website. The full report is you have to pay for it, but it shows mainly that we are increasing a lot both in residential and front of meter applications, and there has been also an important increase from 2017 to this past 2 years also in commercial and industrial applications, which are becoming more relevant. So we have a progressive increase here. We are mainly focused on residential and based on the policies that many countries are doing here, mainly France, UK, Italy, and Germany, which are leading the deployment of energy storage applications, excluding pumped hydro, as mentioned before, and commercial and industrial applications are becoming more relevant in the past years. Okay, so this is also an important graph. As you know, the pumped hydro systems have a complete different dimension at the European level. So we have about more or less above 55 gigawatts installed at the European level, and an important capacity which is over 500 times the one that we have on energy storage, but there is a lot to do as well. As you see, the forecast for pumped hydro installed facilities is also in the future interesting, with some increases in European countries. And finally, as a graph that I like a lot from one of my colleagues, Luis Santos, here in Spain, is that the market has, in terms of development, three different axes, as we see. So we have, of course, the technology readiness level, as you may be related to. But we have also two other axes that are important to be considered when we talk about a technology and a market penetration. We have customer readiness level and also regulatory readiness level. And the path from the German part, the origin of our technology toward markets, has to consider these three different axes to succeed. So what we have, drivers from technology, well, performance and cost are improving constantly. So sorry, that went off. Sorry, so performance and cost are improving constantly. I have some kind of problems here. And we foresee acceptable number for storage applications, as my colleague Mike told before, in terms of cycling, price, scalability, and so on. But also we have drivers on the customer side. Several agents in the energy value chain are thinking on storage solutions for some of the aspects or barriers or problems they are facing. We have more acceptance on the feasibility and reliability of the solutions, and we have an increasing number of pilots worldwide and also at European level, which is important to demonstrate that the solutions are reliable from a technological perspective, but also from a market and economic perspective. And finally, we have a lot of drivers, and this is probably the main change in the past years in regulation. We have the clean energy package and the important commitments that the European Commission is making at the European level in terms of well, carbon emissions and renewables implementations and so on, which drives a lot storage as an important solution to this market. Local flexibility markets appear as an opportunity for energy storage as well, and an important development in many countries that are also pumping in other ones that doesn't have this kind of framework. These sandbox frameworks are enabling new pilots to assess these new business models, and this is an important part to somehow show to the regulators that energy storage is a good solution for some of the barriers we are facing in this energy transition. So that's all. Thank you for your attention, and I will be glad to answer questions if you have.
Thank you very much, Enrique. This is Anastasiya Shapochkina from EDF. I work with Yves, and we are going to continue moderating together. We have one question. We have several questions about this part, and especially I would like to start with the technical questions. So I don't know if we have more about economics. One is, in order to facilitate the study and integration of all these technologies, Mark, I think it's for you, but then Enrique, feel free to hop on. What is your position on the emerging national data hubs, not only retail data hubs, but also grid data hubs? And what's the foreseen rollout? Maybe Mark, you start, and then Enrique can pick up from Mark.
A tendency to favor physical developments over digital developments for a number of reasons. One is because we live in the real world, not the digital world. The second one is because virtual innovations, they optimize what's there in reality. We need something to be there in reality to be optimized. The various data hubs that are being developed do have great opportunities for optimizing things, but there have got to be things there to be optimized. And therefore, I think that the priority should be on getting the right range of technologies available on the grid. People are optimizing them in various ways. There is a hazard with having a national center in that it's going to be set up with the particular outlooks of one particular group of people, which might not correspond with the way others see the market's needs and benefits. On the other hand, there's a great big benefit in being able to increase across the whole national market. So I think I'll leave that one there because it's a number of questions up in the air.
Thank you, Mark. Enrique, do you have anything to add?
No, I fully agree. I think that the energy world is transforming a lot, very rapidly, also to a digital world. But of course, we don't have to forget that the energy is physical, and physics domain that is important. And of course, data hubs will be a relevant tool for improving and for making reality new business models or new possibilities in the energy arena. But of course, we have to bear in mind that physical world remains, and that should be something that should help us to continue growing in this energy scenario, to help improve technology, help improve energy efficiency and operation efficiency, economics as well. But this is an extra tool from my opinion.
Thank you, Enrique. Another question for Mark about technology. You didn't name hydrogen among your storage solutions. How come?
Because we're looking at electricity storage. If you're looking at electricity storage, you're looking at the cycle electricity to store to electricity again. Now, if you put electrolysis and combustion of hydrogen into the mix, you've got a theoretical maximum efficiency in the high 30s%. Right now, they're down in the low 20s% efficiency, with plants that's innately vastly more expensive than anything else that's in the system at the moment, including generation with carbon capture and storage, which is itself prohibitively expensive and inefficient. So I don't see hydrogen being in the mix for the cycle, electricity to storage to electricity, except in specific applications such as fuel cell vehicles and things like that, where it does have immense benefits over batteries, not least that it's not resource constrained.
Thank you, Mark. We'll just to give Enrique a chance also to address this. Enrique, your point.
Yeah, well, hydrogen will become, I think, a carrier as well as many others. As well, Mark didn't tell anything about power to X as well, which is something that is already mentioned in the energy arena. So this is not exclusive, of course. We are talking about the scope we have as work in the working group, but I think that both of them, power to X and also hydrogen, will play a role. But as Mark points out, where it makes sense from the perspective of a technological solution and of course of economical feasibility, we don't have to forget as well that this should make sense in terms of market readiness, and market is driven by economics mainly. So this is something that should be taken into account very deeply when we talk about each technology. And of course, hydrogen will have a role. European Commission is also investing in that a lot, because their forecasts say that there's something specific applications where it should be a market gap covered by hydrogen, but as long as it makes sense from an economical perspective.
Thank you, Enrique. We are now going to turn to our next topic. And we just heard from Mark Howitt, Storelectric CTO, and Enrique Morgades Prat, Head of Market Development at CIRCE. And thank you for your questions. And we're now going to turn to our next presenter, who is back with us, Luigi Lanuzza. Had a little problem with connecting. Thank you, Luigi, for joining us. Luigi, do you hear us? Can you speak?
Yes, I can hear you. I hope you hear me. Okay.
Excellent. I hear you. Excellent.
Oh, worked.
Okay. Luigi is head of new technologies at Enel X, and he is also ETIP Batteries Chair of Working Group 6, which also happens to work on storage and stationary storage, especially. And Luigi is going to present to us the activities of ETIP Batteries and especially the activities of Working Group 6, with which we cooperate, so that we have a larger picture, broader picture of the ETIP and of cartography of what exists on storage batteries. I'm going to share my screen, Luigi, if you want this. You don't have to.
Okay, fantastic.
Can everybody see my screen?
Not yet.
Not yet.
No.
Okay, now it starts.
It's coming. Perfect.
Here it is.
Perfect. Here we go. So, oops, sorry. It should be there. Do you still see it?
Yep.
Perfect. Okay, Luigi, go ahead.
Okay, so first of all, thank you a lot for this invitation. We are working together since a while now, and we really appreciate your inputs. If you want, we can pass to the next slide, which is about the overall view of Battery Europe. Basically, in this slide, we tried to represent all the initiative. Can you go back? Yeah, this one. All the initiative ongoing. Everything started from the European Battery Alliance in 2017. By the impulse, let's say, from the European Commission, which recognized that the great disadvantage actually we had with other countries, mainly Asian countries, in what concerns the manufacturing of batteries, a strategic sector, of course, with a lot of electric vehicles which will come in our roads in the next few years. So this gap must be fulfilled ASAP, because otherwise the whole industry of automotive, but also stationary, of course, will be impacted heavily. No? The European Battery Alliance was thought to support all the supply chain, the missing supply chain, unfortunately, in Europe for batteries, from mining activities, even raw materials manufacturing and operation on them, up to the later steps of the supply chain, so recycling, end of life, and of course application, which is the part of our specific interest. There is also the strategic action plan from the European Union in 2018. These two main drivers led to the definition of some needs required by the starting industry of battery in Europe. How it changed the last year, let's say. In 2019, started Battery Europe's with the slogan, let's say, it's the one-stop shop for battery R&I community. Basically is about supporting the information exchange, the priority setting for the industry of batteries, and generally speaking, the cooperation between all the stakeholders in this supply chain, with a focus on R&I activities and TRL not so low, let's say. Typically, project ranging from 4 up to 7 is something on our interest. And this is for R&I in the short medium period. Of course, there is also battery 2030 for the long period. And what else? The European Battery Alliance now is focusing the ABA 250 on industrial projects, so a project to be developed in the short period, and the real industrial project with a significant commercial value through the business investment platform, a platform created to support all kind of battery project, again, from mining up to recycling. We are in the middle of this configuration of initiatives, and of course we deal a lot with what concerns R&I, so Horizon first 2020, now Horizon Europe project, supporting with some fish for the next coming course on battery, of course, but also key performance indicator. You will see in the next slide this. We deal also with instances like the IPCI, the important now, because the strategy and the other initiative. Then in this slide, some definition more about Battery Europe. As I told you before, both the European battery industry is the main driver. Then sharing information, promote also information not only about the technologies, but also about financing, funding, how to get it from the European community, for instance, cooperation between the public and private sectors, and also regulatory framework is something very important with the sharing of best practice. Then by means of working groups, we are working on the R&D development, the roadmaps, I mean, and on the strategic research agenda. This is really ongoing now. Knowledge sharing again, and the last point, also make this knowledge available and updated for all the stakeholders. Then how we are organized, there is a general assembly including all the association, industry, research entities, delegates from the European community, which basically approves the general decision, no, how to proceed with the works, approves also the governing board, and the delegates, no, for making the decision process. The governing board basically is a steering committee with some delegates from the industry and from the research entities again. The management board team, sorry, is a kind of board for coordinating the several working groups. And it's facilitated by the Secretariat of the Batteries Europe. Then the thematic working groups, as I told you, there are slides about them. We are divided in 6 working groups. You will see the details in the next slide, and also the national and regional coordination groups. We can go, I think, to the next one. Can you pass to the next? Okay.
I did. I don't think you can see it. Do you?
Yeah, now I see it, yes.
Yeah, perfect.
Sorry. So a bit more information about the activities on working group. There are a lot of material available to go more in deep in the contents, but generally speaking, working group 1 is really working on R&D topics. A lot of the members are also participating to the work activities of Battery 2030, for instance. Also the most famous colleagues are there. So it's about R&D items, but it's also about making a benchmarking of the different several technologies which will come in the next years. WG2 is about materials and recycling, and I would like to underline recycling is a very important topic now. Also economic topic will be a differentiated factor with the industry of other parts of the world. So you see here a certain grade of highlighting on items concerning end of life and the use of materials. Of course, is about how to make this material or these second life modules available, how to work on these raw materials, while the application is more on WG5 and WG6, no, of these, for instance, second life batteries. WG3 and WG4 are working on again on materials and modeling, but is basically work on the cell level of the system about materials, and also of course design of the cell for achieving the highest performance we aim to have since the beginning in this new growing industry in Europe. So this will be another differential factor. We have to recover some time compared to the Asian countries, and we will start with really innovative technologies for making this product competitive. Otherwise, we are not working, and we are not working well. Let's say we are not winning since the beginning, of course. WG5, WG6, we are working about application with the application of stationary in case of the WG6 and the mobile application WG5. So you see some items, some are common between WG5 and WG6. For instance, the usage of second use in case of WG5, or second life in case of stationary application of modules from EVs. No, the difference, of course, is that when we consider the interaction with the battery inside a vehicle, it's up to the mobile application. When we consider how to use them for the grid, it's up to WG6. Is a fixed battery once you connect to the grid. No. But the difference comes where, again, we speak about how to charge. Fast charging is a topic for WG5, while we deal with a lot of use cases for stationary usage mainly. There are also transversal task forces you see on the bottom of the slide. Sustainability for sure. One more important topic which emerged was also safety. Because here perhaps we are a bit again in disadvantage, not so up to date compared to some rules already in place, for instance in US. So UL and the IEEE are the very likely the most advanced standards for safety, and we need to fill also this gap. And again, business model is another topic to be considered, again with education, very important, since the beginning of the activities of European Battery Alliance, this was underlined that we are also missing technicians, but also engineers specialized in the industry of battery at every level of the supply chain. Okay, I think we can go now to next slide, sorry, which is about WG6. What we're doing. So the scope of our work is integration, application and integration of batteries for stationary usage. With our mandate, we have also to identify research priorities. We're not considering again only the batteries or the DC side, but the system as a whole. So concerning also converters, but every system which enable ESS to connect to the grid and provide the services to whatever customer, either a TSO, either DSO, either an end customer, residential customer, or even how to integrate with a power center, no, to a power plant, if integrated with generation. Identify the needs and also try to understand how to use for a second life the batteries coming from mobile application. We have several stakeholders, both industrial and also research entities. You see again in the bottom takeaway, there are a lot of participants now. There were 25 research entities and 27 industries, but we're still receiving application, and we are happy to have really good people on board. Experiences so far is very good, I have to say. Of course, we have also delegates from the European Commission, which are steering, are providing suggestion, and also very collaborative also them. Next. Can we pass to the next slide?
Yes, you should see it.
And yes, and the activities. So the first activities we received, the first request of activities we received end of last year. They were about the KPI. We had to review the former set plan KPIs, the ones for 2020. So review the values, understand if such targets have been reached or not, understand if some of these KPI were really a need, or were required from the stakeholders or not. Even introduce new KPIs in case we would find someone applicable. Then, of course, proposing target values for 2025, let's say, and 2030 was part of the scope. Very important also task 2, Enel and I fish for the upcoming Horizon program. You will see that we, after a long process, but in a short time, we found someone and proposed to the European Commission together with our other platforms. And the definition of use cases. Now, this third task, in order of time, is also quite important because actually it should be the first. No, starting. Our proposal was we start from the application, we start from the need of the market, and we go to the KPI, for instance, which is needed, and then this KPI becomes a KPI for the other working groups, for who make cells, for even who make the technology of the future. And we are now at this point. Even if we started for T1, we completed T3, and then we are coming back to KPI in some way, crossing the use cases to the KPI. And we are working right now to the strategic research agenda, sharing the information also with WG2. We are drafting now the first 2 pages of the strategic research agenda. Okay, then a little bit more detail on T1, T2, T3. As I said, we had to review the set plan KPIs. propose a new one. We did this exercise under 4 dimensions: performance, so really technical parameters, cost, manufacturing, recycling, safety, and sustainability. Several parameters, not only, of course, technical, not only about performance, but also about sustainability, for instance. What we found out is it's more than 20, it's 24 as of today, but this is a process which will have several phases of review, and let's say now are 24 that are too much. We also have been said, no, because it's not usable finally if you have to think if you had to propose 24 KPIs for a single call Horizon 2020. Of course, it's not applicable, it's not feasible, and not usable finally. So the exercise we are doing now is crossing these KPIs with the task 3 outcome, the use cases, starting from the division of the electricity system in the transmission, the distribution, the end user side, the demand side, let's say, and the perspective of who is producing electricity. These 4 sectors have their needs, their services to be satisfied through the use cases. These make then straightforward a selection of relevant KPIs, few of them, not 24 every time, for the relevant application, and also solve another issue we had in the first task. So if we are proposing a KPI, let's say for charge discharge rate, no, I hope to have a fast battery in 2030. But I cannot ask in the meantime for having a lot of energy density, for instance. No, this is one of the first discrepancy which came out. Of course, it's the use case is relevant. Then in case of a fast application, I will ask for an high C rate, but I can accept to have a less energy dense battery. Even more clear in the case of LCOS, the cost levelized cost of storage, which is even dependent of a project side, but is still a very important key parameter when we want to compare application to application, solution to application, so solutions to solutions. Sorry. So we need to define a set of KPIs, and this is the new job of refinement of the solution we are going to do now. And then finally, the proposal for the European calls. We found 6 of them. Just to say that we started for a broad base of proposal, and we tried to integrate every one of them. Perhaps we have some concern with time. Did I went out of my time, or there is still time? I don't know. Okay, just to tell you that finally we integrated more than 33 topics in 6 topics. The first 3 are very broad, comprehensive, a lot of attention about digitalization of the batteries, but also on safety and also of interoperability. These are the most important items which emerged across all the proposal. And that is from my side, I think. Open to question. Let me know how many, whatever information you need, know if we can answer. Hello?
Hello, Anastasiya.
Thank you, Luigi. Thank you. I have a sound problem. It's getting cut by the machine, I think, from the web by the WebEx software, unfortunately. So automatically, basically, just several questions for you from our listeners. Thank you very much for this very clear presentation about ETIP batteries activities. there are questions about how do you figure out to include all of the foreseen storage capacity onto the and then also the it's about the definition of stationary storage. Maybe we're going to start with this one. How do you define stationary storage? Is it in a technical way, so to say? Does it mean the steady state system behavior, or does it mean anything else?
Yeah, basically is whatever storage which is only supposed to provide service to a grid or to the demand side, to an end customer. And so the division here was clearly between the battery, which are serving also mobility in a broad way. I mean, WG5, for instance, is taking care of batteries for electric vehicles, but also for ships, also for even aircraft. So aviation. This is something growing now with a lot of drones, AGV, with batteries, lithium-ion batteries. The difference is basically this, if it moves, let's say, it seems a joke, but if it's something that can move, it's about mobility. If it's really only a battery static for power plants support, for residential even, so small one, for commercial industrial, but installed and fixed and connect to the grid, that is the stationary. This is basically the difference.
Okay, thank you, Luigi. Maybe just a little comment about the cooperation between ETIP Batteries and ETIP SNET, which we started a little bit, and what issues the cooperation goes on, and how do you foresee it going forward?
Well, we found with just a couple of calls we had at the beginning, and now the process is ongoing. We found some difference in the difference. I mean, is that ETIP SNET has clearly a broader view because it's about several items, and while ETIP Batteries, battery use is really focalizing only on batteries application, either for vehicles, again, either for stationary usage, but it's about batteries. And I can tell you that it is currently heavily focusing on lithium-ion batteries, perhaps less than European Battery Alliance, which is only nowadays thinking about lithium-ion batteries, because that is the first product we aim to have in Europe. Of course, if we speak about activities of WG1, WG2, WG3 in ETIP batteries, also other emerging technologies are really evaluated in deep. But anyway, it's more only focusing on batteries, while ETIP SNET has a broader vision. So what came up from this reflection, that we need the input of ETIP SNET for sure, especially if we speak about the use cases, especially if we think to integration task, while we can, I hope, give support in definition specific parameters for the specific application.
Thank you very much, Luigi, and thank you for this presentation. We're now going to turn to the what we can say is the second part of the seminar. So the first was the introductory part about the organizations, the two ETIPs dealing with stationary storage, and also the overview of the stationary storage technologies and markets. And now we are going to look more closely at maybe first basically the technico-economic analysis of storage technologies, and then diving into the technical different types of technology. So Silvia Bodoardo will talk about lithium-ion, Ramon Guerrero on V2G, Michael Willemot on inertia, Mark Howitt on compressed gas technology, and Yulong Ding on liquid air storage, energy storage. And so we're turning now to the expert from EDF but for a presentation on technico-economic analysis of storage technology. This is Etienne Sorin, EDF R&D expert. I'm going to share the screen. Etienne, are you ready?
Yes, thank you, Anastasiya.
Let me know when you see the screen.
Yes, I see it.
Perfect. There we go.
Thank you, Anastasiya. Hello, everyone. So my presentation is going to be a bit in between Mark's presentation and Enrique's presentation. So I'm going to talk about technico-economic analysis of storage technologies. And to begin, if you can move to the next slide. From Mark, you had the many drivers of storage technologies from the energy balance aspects to the inertia requirements that renewable penetration is going to put stress on. And from Enrique, you had the future market overviews, and my goal here is going to explain to you a bit a way to take into account the drivers and to provide a way to compute the market overview. So I begin with one of the drivers that is why we talk about storage today, is the technological evolution and the maturity of the battery, but we will see maybe in a few years for other technologies. That translates into a price decrease that we've seen in the past decade of approximately 20% every year. And this translates from the overview perspective, if you can move to the next slide, into a view of how the storage is going to develop in the next 10-20 years. Here is the overview is provided by Bloomberg New Energy Finance, and it's provided annually and by installed power. And what you can see in this overview is that it's divided by applications and by connection levels somehow. So it's already a view at one of the approach to deal with that is that we need to go much deeper into how storage is going to answer to the technical challenges provided by renewable integration. And we need to understand how the market is going to be, the electricity markets are going to be affected, and what are going to be the economic signals that will translate later into storage evolution. The next slide is a quick description of how the different applications will interact with each other. You've already had a quick talk about that from Mark, and the main point here is that if we look from the application perspective, the applications that storage can provide are not uniform. There's many different parameters that describe each application, and from the technology perspective, there's going to be many different technologies that will have the characteristics that match either perfectly or good enoughly these applications. Here, one of the axes that we mostly talk about is either the response time or the duration of the service that is needed. At the bottom, I've provided two examples of these applications. One that is rather energy related, that is the auto consumption application for storage, where we try to maximize the self-consumption of the auto consumption of a consumer from a PV panel. And we can see that this is rather a daily application where we're going to charge and discharge for several hours. On the right, it's the frequency regulation. Here is a show of the primary reserve, where some assets are contracted by the grid to react very quickly in a matter of 30 seconds to counterbalance power imbalances on the grid, and to prevent the frequency from deriving from the 50 Hertz value. And we can see that this application, it's a much faster in terms of response time. Here you can only see a few minutes of the application, and it also requires much less cycles of much less energy to provide the service. So we need to understand well the characteristics of these applications, and then we need to also understand how these characteristics are going for storage to translate into market and economic consequences. If you can move to the next slide. I think you can, because there's some animation, you can move to the end. It's going to be easier because I don't have the control. Yeah, thank you. Yes, so I wanted in this slide to provide a quick, very schematic example of one of the applications. It's very simplified, but it's a good way to present how storage is gonna make money on electricity markets, and what are the drivers that could provide uncertainty on those revenues. Here, the application is the market arbitrage, where we try to charge on off-peak price, on low prices, and we try to discharge on peak prices. And we usually think that we can cash in the price spread between these two prices. But the first thing that we need to take into account is that there is also some storage losses from the storage, and that these losses are going to reduce the price spread. So in order to compute the storage revenue, we need to subtract what is needed to cover the losses of the storage. Of course, the yellow arrow that I put on the graph, it depends on the losses of so it depends on the technology, but it's also going to depend on the charge price. And when we compute the storage revenue in the green arrow here, what we also can show on the graph is that here the storage revenue is a price in euro per megawatt hour. If we take into account all the capex and opex that a storage technology needs in order to perform over the whole lifetime, and we bring it back to a price per megawatt hour that the technology has cycled through, we can kind of compute an equivalent of the LCOE, the levelized cost of electricity, that is computed for usually for generation applications. Here it's the orange arrow, and we can compare then the discharge price with this LCOE equivalent. And this gives us a quick approach to understanding whether storage technology is going to be profitable or not on arbitrage application. And then on the right side of the panel, I wanted to show quickly how market uncertainty can affect the revenues of the storage. Here, the example is a peak price drop. If compared to what was forecasted at the beginning of the lifetime, the peak price is going to drop by say 10%. What is the impact on the revenue of storage? And to understand that, there is a numerical example at the bottom, where if you charge at 20 euros per megawatt hour and you discharge at 50 euros per megawatt hour with an efficiency of 85%, a drop of 10% in the discharge price is going to translate in a drop of 19% in the storage revenues. That's a very schematic example, but it's a good way to understand the drivers at stake here. And so we see that having a light view of the electricity markets and the prices, it's not going to be good enough to understand the risks underlying the economics of the storage, and understanding how the storage is going to make money and to be able to enter the market. A good way to show this on historical data is to compare, for example, the average price on here, it's on the French day-ahead market. If you compare the average yearly price from 2010 to 2019, and you compare it with the revenues that a 6-hour storage can get on this market, you can see that it's decorrelated. Yeah, there is no strong correlation. So we need to look a lot deeper into how the market prices are structured to understand how the renewable penetration is going to impact the storage revenues. And so to do that, what we need is a very systemic approach. If you can move to the next slide. Same, you can go to the end of the slide, it's going to be easier. And what we usually do for that is that we need to have a modelization not only of the storage technologies and the market, but we need also to be able to model all the competitors for storage on the flexibility markets that storage can access. And here I've put on the left some of the examples of the parameters that we're going to take into account for this modelization. For example, we need to have a very clear modelization of the variable generation, not only the hourly load factors, but also maybe the location of the variable generation to take into account maybe grid aspects. And we also need to take into account the forecast errors to understand how these forecast errors are going to translate into market prices on the and also on market liquidity on very short-term markets such as intraday markets. On the other hand, we also need to model other competitors such as demand response. So we need to have very clear modelization of the demand, but also how it can be modified to reflect on the flexibility needs. And we need a good modelization on the dynamic constraints of the generators to understand how the renewable variability is going to translate, who is going to be able to respond to this variability. And of course also some macroeconomic parameters are needed, such as the fuel cost, the CO2 prices, and so on. And when we compute all that and we put on top of that a storage, a dispatch model and an investment loop, we can provide what's a good approach to model the storage revenues is the price series. We can provide the revenues for storage, but we can also understand how storage is going to impact the revenues of storage. So how it's going to have an effect on the market prices, and how we can model also how it's going to what we call cannibalize the position for future technologies. If you can move to the next slide. This is my final slide, and it's just an example of this kind of simulations. Here we try to model the space for a weekly storage in a 60% renewable generation in Europe, where from this 60% there is 40% of variable renewable. And what we see is that we can compute on the blue line the revenues for storage. So it's again a quite schematic view, and the results are much more complex than that. And when we add to these revenues the costs for storage, and so to take into account, we need to take into account price forecasts of storage capex, and we can compute what is the likelihood of having positive revenue given a penetration for storage. And we can see here, for example, in the UK, there is a good likelihood that there's going to be a strong position for storage for maybe several gigawatts. Of course, maybe not all competitors for storage are taken into account here. So these results have to be taken carefully also. But we can see also that on continental Europe, there's going to be a much less space, and we can also see the depth that is very limited for storage. Thank you very much. If you have
Thank you
any
very
questions.
much, Etienne. Thanks very much for this intricate analysis of the storage approach to the storage profitability, and which I think complements what Enrique presented us about the markets. Thank you. And we are going now to switch to the technologies in particular, and especially we're going to now give the word to Silvia Bodoardo, a professor of Politecnico di Torino, and who's going to talk to us about lithium-ion technology as well as other battery technologies. I'm going to open the presentation, or Silvia, if you prefer, you can just take over maybe, because I have only the PDF version of your slides. If you prefer to have the PowerPoint version and to project your screen. Silvia? If Silvia is not with us, maybe temporarily. Maybe we're. Ah, yes, here we go. Silvia, you're with us. We cannot hear you. Silvia, we cannot hear you.
Okay, can you hear me now?
Perfect, this works.
Okay, yes, because my microphone was off and I couldn't switch it on, so I was clicking. Okay, so you should see my presentation. Can you see my presentation now?
Yes.
Okay, perfect. Thank you very much for the introduction, and thank you very much for inviting me and give me the opportunity to present this topic that is more focused, is more chemical one. So, so I will skip this because everybody already knows that the renewable energy new installations are growing up, and we can say that storage can be the holy grail for energy transition. So everybody already, this was well presented before than me, and so everyone knows that this can be an help in order to move toward energy storage. So there are several opportunities, several ways to store the energy. Something was already said, and I want just to say how the batteries are now in the middle if you consider specific power and specific energy storage that battery can give us. So fuel cells are mainly systems for very high specific energy, but if we want to store a lot of power, get a lot of energy altogether, you need to move to supercapacitors. So battery are something in the middle that can be, whose rectangle, this green rectangle can be grown up and is going to be growth considering the new development we are going to get today in the field of batteries. So let's go to see what is a battery today and how is done and which are the components, but most of you already know, but I just do some sort of chemistry lesson for everyone. So you know that batteries are composed by two electrodes. One is the cathode, which is the one containing the high voltage active material that is always mixed with some carbon and some binder keeping together these particles. The active material is commonly composed by a heavy metal that can be nickel, manganese, cobalt, and so on, and bond to negative species like oxygen or phosphates and whatever. At the anode, we have commonly graphite in the lithium-ion configuration, and you can get also metallic lithium in lithium metal battery configuration. Between the two, we have to close the circuit. We have the lithium conductor that can be a liquid where lithium ion can move through, and also solid, as I will show you in a while, and with a lower and more difficult conductivity, lithium ionic conductivity, for sure, than electrons are moving outside. So which are the main parameters where we have to focus more our attention considering the so-called perfect battery? So we should get all these pentagons filled with so that the best battery should get very high energy density, very high power density, together with low costs, but also, as Luigi mentioned many times, very high safety, and also to be green and sustainable, so recyclable and so on. So what on what can we play in order to reach all these parameters together? If we are speaking about high energy and high power, we can, for example, increase the voltage, as just to remember that energy is the product of capacity by voltage and power is the product of current by voltage. So increasing voltage, we can both increase energy density and power density. If we increase the capacity, we are going to increase the energy. So we can play on these two parameters in order to have the highest energy density as possible and the highest power density as possible. We can do that changing materials, so we have a lot of different possibility in materials with which we can build our batteries. Because when we speak about lead-acid battery, for example, we are speaking about one single chemistry. When we are speaking about lithium-based system or also even other alkali metals batteries, we have a very big family of possibilities and alternatives. So we speak about cathodic materials, we can play and gain a lot of in voltage. So if we move from iron going through manganese, nickel, and so on, the voltage is increasing. As just an example, today the most used cathodic material is NMC, which is a combination of manganese, nickel, and cobalt, with different amount of relative amount of all these three heavy metals, and so lowering the amount of cobalt as much as possible to meet the environmental issue aspects. But so that if we can go on this line to reach the highest voltage as possible. If we speak about cathodes, we can move on the other axis, on the x-axis, in order to increase the capacity. So just an example, if we move from graphite to metallic lithium, we are having 10 times higher capacity. So it means that we can really get much better batteries. What we would like to get is something that stays here, and to get the highest voltage as possible, together with the highest capacity, in order to have the best system. But you can see also here there are some new elements that are arriving, on which I will say just one word later. So this is today. So we have many opportunities already playing with chemistry today. But what is going to happen in the next future? So in next future, we can again consider many different chemistry. This is just the list. Again, chemistry lesson. Let me be the professor here. So this is the series of electric potential. So as you can see here, lithium is the one chosen as it has the lowest reduction potential. It means that when I couple lithium with any other possible cations, cathode materials, I have the highest difference in voltage. It means higher is the difference in voltage, again, higher is the energy density. So you can see if you have carbon, you have a lower energy density, but then you can also move toward completely different systems, such as oxygen, for example. Oxygen has a much higher difference in voltage than all the others you can have here. Moreover, oxygen is also very light. It means that the energy, specific energy, is jumping up to 10 times, the theoretical one, 10 times then the one of common lithium-ion systems. But this is really far in the future. It's something that needs a lot of developments, needs a lot of work done at very low TRL in order to reach it in the future. This is something in the frame of Battery 2030, as Luigi already told before, in the frame of these European activities. But another system, another element, another cathode that is going to be very close to market is sulfur. Sulfur is very simple, as it is, just to say, really fully available. And nevertheless, the difference in voltage is much lower than the one of any other lithium-ion cell. Its reduction takes 2 electrons. It means that the capacity is much higher than the one of any other system used today as a cathode, and this makes the theoretical energy density to jump to 5 times than the one of any lithium-ion cell. So lithium sulfur is still a very interesting system. Let's consider that sulfur is really high available, we have too much solar, very easy to get, and it's also a sub-product of the production of oil, for example. So there are oil companies that are really very interested to use this sulfur coming from oil production as a waste and to use it as active material in batteries. Sulfur is a circle of 8 atoms. While reducing, this circle opens and you have the insertion of lithium, so that at the end of this project, these are anions, and so these ions are all soluble in the electrolytes. And then the final step of this reaction is the deposition, is the precipitation of lithium sulfide, Li2S. The drawbacks, this system is very interesting. You have, as an anode, you have simple lithium metal, but you have some drawbacks to be overcome. That is, on one side, this polysulfide shuffling, the movement of this polysulfide in solution, so that we have to block the polysulfide, and it's a lot of work done in this field, and also the high reactivity of lithium. But really, this system, even by a manufacturing point of view, is very close to the one of lithium-ion systems, so that it's also easier and to be produced and closer to market. There are also something very far, but still very interesting, on which everyone is working, is the use of other ions than lithium. For example, sodium can be really well used. Sodium has a lower voltage, and also is heavier than lithium. This makes it that the gravimetric energy density is lower, but its availability, abundancy is so high, and the earthquake, the earth crust, that really can be of interest, in particular for stationary applications. But also multivalent cations are coming in the market, as magnesium, for example, as you can see here, and aluminium, which has very interesting properties, but it's very difficult to make aluminium up to now to work because of because its ion has 3 positive charges. So we spoke about, you remember, energy density and power density. Another very interesting parameter and very important parameters is safety. So if I told you before, we have to increase voltage, but we have to increase capacity. So we can move from graphite to metallic lithium. Metallic lithium is really very interesting because of its very high capacity, but it is very reactive. So on one side, we substitute lithium using, for example, silicon. Silicon has also another drawback, which is the volume expansion. So it becomes hundreds of times bigger during reduction, during lithium insertion, okay, but it's lithium reduction still. And so you have to mix it with carbon, getting this silicon carbon composite, and its capacity is reduced as higher is the amount of carbon used. So this is one possibility. The other possibility is to work in reducing the reactivity of lithium, in the sense that while lithium is working in the cell, is cycling, there's the dendrite formation. This dendrite formation can break, getting some isolated lithium that is not more reduced and oxidized in the cell. But these dendrites can also grow so high, so much that they can reach the cathode, getting a short circuit in the cell. So the way to reduce these dendrites is substituting the liquid electrolyte, for example, with a polymer electrolyte. So the polymer electrolyte can be classical polymer electrolyte, or also nanocomposite polymer electrolyte with the use of ceramic compounds, which are acting mechanical blockage of these dendrites growth. so that they are blocked when writes, and this makes the cell to be much safer. Even if the conductivity of lithium inside the polymer electrolyte or solid state electrolyte in general is much lower than the one in the liquid electrolyte. But the other advantage is that, as you can see here, the thickness and the volume, the total volume of this cell is much lower, so that on one side the gravimetric energy density increases, but on the other side also the volumetric energy density is strongly increasing. And this is very important, in particular for mobile automotive applications, where you have also space to consider. But within Battery 2030 initiative, we launched the new ideas. On one side is the use of self-healing system, materials, electrodes, and electrolyte. It means that our system there are materials that can be repaired when they are broken. So if you have some damage in the cell, you can self-repair. This material can self-repair, and this is very important by the safety point of view, and also the insertion of smart sensors directly inside the cell, so that a lot of parameters can be considered and monitored, sensed. And these parameters can be, on one side, the temperature, and if you measure the temperature inside the cell, you have a much more precise measure of the temperature, and any drawbacks, any issues can happen, are detected really at the starting point. On the other side, you can evaluate volume expansion, so you have the ability to study the SI layer formation and so on. It means that this will give a huge number of data, and this will be reflected also on a more complex BMS, battery management system, so increasing complexity, but getting a strong effect in the increase of safety. Okay, so I'm just concluding here. This is a very fast overview on the future of battery. I hope I was not exhaustive. I well know this. And
we'll need to jump to conclusions, Silvia, because we have still, we ran a bit over time.
I was just only thanking the task force on batteries in Politecnico and my group. And now all of you for your attention.
Thank you so much. It's a really fascinating presentation on a perfect battery, which is at the same time highly performant, self-healing and safe, easily accessible everywhere in the world, and cheap. That's these are the challenges pretty much in a sum that you drew for us. And the difficulty is that this is still kind of to find. And of course, in the chat we have the questions about the which we do not have time for questions anymore. We'll have to continue with presentations, but of course these are the issues that we're all familiar with about such as the accessibility of lithium and the problems connected to the current technology, which is the most dominant on the market. But thank you very much, Silvia. This was fascinating. We're going to now turn to Ramon Gero. Ramon is R&D engineer at Istituto Tecnologico dell'Energia, and he's going to talk about vehicle-to-grid in energy system storage. Ramon, if you see the function which allows you to take over, please use it, because I do not see it anymore on my computer. It disappeared. I think it's when it goes toward the presenters, then I do not see it anymore. Ramon, so if you can take over your own presentation, take over the screen.
I don't have the option here.
Okay, perfect. Now I have it back.
Okay, now.
You got it? Go, perfect. Go ahead. Take it.
Can you see my screen?
Yes. And
the presentation?
I know the light is very unfair for the following 4 presenters, but it's for the sake of your own sake, basically, is just basically try to go for the jugular, especially those who have numerous slides, multiple slides. Just make sure at least to stay within your time limit. And I think we're going to go over time, but especially for the sake of the basically the audience, if the audience will start dispersing. So if you can be to the point, that'd be great. Go ahead.
Yeah, okay. So, well, my name is Ramon from ITE, from the Technological Institute of Energy in Spain. And we're talking about smart charging and vehicle to grid and vehicle to home technologies in order to like energy systems in the electric grid. So as a little context on the necessity of these technologies, we have the flexibility necessities and uncertainty related with the decarbonization necessities and the integration of renewable energy. And as it was already mentioned in another presentation, so we need to balance in the generation, the renewable generation, with the demand. So this leads to the necessity of storage systems in the grid. And on the other side, we have also another of the main pillars of the energy transition, that is the electrifications of sectors that are now being really polluting or were formerly one of the main sources of polluting. This is one related with transport and the electrification of the transport sector and mobility, and the deployment of these kind of transport is one of the pillars of the decarbonization also. This leads to a massive energy demand, electricity demand for the grid, and the challenge of the electric vehicles integration in this grid, and how to manage all the demand and the power peaks that are related with the charging process. But this can be also be seen like an opportunity and a solution, as they are also mobile energy storage systems that can be that we can take advantage in order to give this energy storage system that the grid needs for the balancing services. But here, and if we want to use the electric vehicles as mobile energy storage systems, we have also the challenge of the uncertainty of availability of the flexibility of these electric vehicles. So why is this flexibility important? It is important because it links to two of the main pillars of the energy transition, that are the balancing of the energy system with high shares of renewables, and also the necessity of the electrification of transport. If we take advantage of these cars and these electric vehicles as energy storage systems, we have to face also challenges like maintaining the EV batteries durability and the EV users' comfort. And these smart charging and vehicle to grid solutions have to take into account these issues also. And about the economical issues related with these technologies, we see that we can have economic savings related with the investment that would be for the objective of spinning reserve and stationary storage systems for balancing, and also the investment, the potential investment in grid infrastructure improvements in order to avoid these congestions that can be produced by the EV integration. So the savings from the avoidance of these investments can be an economic advantage of this technology, and also new incomes for the EV users related with the flexibility that they can provide can be another income source for these EV users, and can be also a good way in order to make more profitable the electrifications of the transport. In this sense, our solution is related with these technologies, smart charging and vehicle to X, vehicle to grid, or vehicle to home technologies, which are related with the bidirectionality the smart charging process. And in this sense, we have to develop charging stations that have the capability of this vehicle to grid and this bidirectionality. And also we have to combine these technologies with algorithmics and intelligence in order to estimate the flexibility of the electric vehicles, related mainly with routes data, forecasting of the smart charging process demand, and also user preferences related with the preferences from the EV users in order to have their vehicles charged. And also the algorithms and the intelligence related with the charging commands optimization and how we distribute these charging commands throughout all the charging stations that we have the possibility to control and to manage. This is very related with the communications issues, and here arises the OCPP or Open Charge Point protocol that give us the opportunity to manage the charging process in a proper way. So all these solutions merge and combine give us the possibility to solve grid congestions and unbalancing problems with these vehicle-to-grid technologies, and also vehicle-to-home in order to give also more advantages like grid stability and also local efficiency for the energy management systems of the communities or households. And all these solutions we validate and test them in a demonstration environment, which is our digital energy lab, in which we have this grid infrastructure and all the stuff related with the charging stations and communication protocols in order to validate these solutions and these strategies. As a summary of the main advantages of these technologies, as we said before, the current energy storage is like big power banks or spinning reserve related with pump station are more expensive to supply and require significant investments. And as the number of electric vehicles is continuously rising, the electric cars can provide a storage option with no extra cost, because it's a technology that is already developed and is being integrated in the grid anyway. Also about the technical advantages, when installing a charging device in a household, the electrical connection can become a hindrance to the EV charging installation. And with vehicle to grid, we can avoid further investment through local peak saving strategies at a local way. And also in terms of the grid stability and the security of supply from the electrical grid, the vehicle to grid concept can improve the performance of the electricity grid in many areas, and can offer services related with reactive power support, active power regulation, tracking of variable renewable energy sources as other potential services that these technologies can offer. And related with the challenges of these technologies and the use of EVs as mobile storage options, we have these three main challenges related with battery degradation, because there is like unpredictable and how the charging process and the vehicle to grid process and all the cycles that these have as a result of this technology in the EV batteries, how they affect the charging and discharging patterns to the EV life cycle and their also their possibility to be recycled. So in these terms, it is very important to have research in advanced BMS in order battery management systems in order to manage and control this process, so as to not affect in a bad way to the life cycle and the life cycle of the batteries of the EVs. Also about the EV users comfort, as we mentioned before, we need user engagement apps and solutions in order to know their preferences. So these vehicle-to-grid technologies and smart charging and how we control from outside the charging process does not affect the comfort of the users. And also security threats that are related with the communications issues. Here we have to take cybersecurity strategies related with ICT and the possibilities that these open protocols give us in order to protect the process, so we don't have attacks from the cybersecurity side. And about these advantages and the challenges that we have mentioned, we can have different target markets for these technologies, different target users, domestic users, EV fleet managers, aggregators, and also DSOs and energy communities for the management of the electricity grid, and also different services. As we mentioned before, we have these vehicle-to-grid technologies can offer peak load management in buildings or in communities with aggregators. Can give services also for the flexibility markets, and the main service that we are facing and we think that have this potential opportunity from vehicle-to-grid and smart charging is the congestion prevention and the supply quality. And this is all from my side. Thank you so much. Thank you for your attention.
Thank you, Ramon. This is a very good overview of V2G solutions and their the related aspects, very much, especially for the explanation of the connection between V2G and flexibility and the role it plays in flexibility. Our next presenter, and I suggest that we remain in this mode when you just take over your own presentations, because it keeps disappearing. I do not have right now, for example, the control, is Michael Wilmot, who is a CFO and a business development director of Oxto Energy, and he's going to present on inertia. Michael, up to you. We do not hear you, Michael. Your microphone.
Yeah,
perfect. It works.
Can you hear me now? Yeah.
Yes.
Okay. So thanks, Anastasiya. Thanks for the invitation today. Yeah, I'll talk about actually two applications that flywheels, which we belong to, can supply actually. So this will be grid inertia, but also EV charging actually. Just a bit of how a flywheel works. So it's a mechanical battery. So it transforms the electrical energy into a kinetic energy of a rotating mass using a motor, and then using a generator, transforming back to electrical energy. So this is quite simple, and the energy stored is just dependent on the speed, how fast you spin your mass, and on the size or the inertia, actually the moment of inertia of the flywheel itself. So a bit of background just about Oxto. We come from the satellite industry at the beginning. So the founder of the company created different subsystems for satellites, and one of them was very small flywheels put on board satellites to replace batteries. For different usage, but also for storage, to store energy, but also to use a gyroscopic effect. Then we brought it back to Earth to see how we could commercialize this technology actually, and that's how the Oxto flywheel came out. Just what the main difference between flywheels and mass and the other. Between our flywheel and other flywheels, but also with other technologies. The particularity is that you have a very long lifetime, more than 20-25 years, with where you have constant performance. So that means that there's no degradation over the lifetime because it's purely mechanical. You have also a limited cycling usage. of the flywheel, which is quite useful in applications with like the one I will mention for EV charging. And also what we managed to do different from other flywheel is that we made it quite easy to mass manufacture. We came up with a very simple design just because we come from the satellite industry, and we managed, for example, to make the flywheel, which is normally a mass spinning around a shaft, and the motor generator be the same. So that's how we came up with a very compact and safe design. And of course, flywheels are part of the circular economy. We use only steel, but can be also carbon fiber in some example for other flywheels. And generally, so it's 100% recyclable, and there's no issue with any hazardous material or mining issue coming from the upfront of building the flywheel themselves. So I'm going to talk going inside the applications directly. So the first one is about EV charging. So EV charging, the main issue of EV charging is not about the energy that is available on the grid, but it's more about the power. So when you need actually to charge, you have some kind of bottleneck on how much charge you can provide, the rate of charge you can provide to EV users. So that's where actually so typically if we take the grid, then you will start having a few cars, and as long as you increase the number of cars and the frequency on how much you have to charge per day, then you have to generally to increase your interconnection costs and infrastructure as well to adapt to the availability of charging in terms of power that you need to provide to these different vehicles. So generally what is done is you take like the chemical batteries and then you reduce your interconnection costs, but then you had all the different costs related to the chemical installation. Whereas if you take flywheels, since it's a higher power density, so we can even provide more in terms of power boosting. So that's how you can even reduce your interconnection cost. And then you reduce your maintenance cost because flywheels are made for have a very low maintenance cost over the lifetime. They are really simple technologies that don't need to be maintained that much, apart from some bearings replacements, and that's the only parts almost that are replaced over 20-25 years. There's no replacement cost over the lifetime as well, and even the disposal, there's kind of residual value in terms of how you can reuse the material that it's made of. However, we see that what will be the real solution in terms of practical application in the end will be using this flywheel for to provide the power enough to remove this bottleneck to feed different cars at the same time, and also wherever the charging station will be located. But of course, there's place as well for other technologies to largely store energy and serve as an energy tank for the flywheels. So we see it as Mark did in his presentation earlier today. It's going to be a combination of different technologies at the end. It's not like one technology will take over the other ones. Second one is about the synthetic inertia, and it's part of the grid stabilization applications to integrate more renewable energy at the end. That's the final objective of all these applications. I won't come back to the different challenges that are met by the grid, so it's been already developed today. So but basically we have some of existing and previously used power plants, like fossil fuel power plants or hydropower plants, nuclear, and they were all synchronized to the grid using the rotating machines. So that's why they have high inertia. On the other hand, we have low inertia. We meet this with the new non-synchronous generators, mainly wind and solar plants, but also with all other everything that is connected to the grid using inverters, for example, the battery systems, even electric vehicles, and so on. So just, yeah, Mark already described it, but what is important with inertia is that you will have a fading effect if you have a high inertia, whereas if you have a low one, it's likely to fall from a cliff. So it's just a big difference, and it makes a big difference for the grid because there's no time to react if you don't have inertia, and that's a big issue. And that's what's happened in the UK last year, but also in Australia, especially in South Australia in 2016-17, during the summer, the whole South Australia was blacked out, and that's how it came all this development of frequency response and also inertia capabilities. That would be, I will come back later on this, but it's a requirement for all non-synchronous generators to provide this kind of capability. And also in North America, there's been different events in the New York area regarding these issues. So yeah, basically the flywheels and will come as potentially an enhancement of the inertia, using also either using purely flywheels or also along with virtual synchronous machines that are actually software parts. But basically they will need the physical capabilities of a flywheel, which is very fast to respond as it's unlimited life cycling. So it's quite interesting for inertia. And ultimately that would be these rate chains. It would be emulating an inverter-based generator into providing capability of inertia. The existing markets just of inertia are very small for the moment. You have a DS3 in systems in Ireland that are one of the services is inertia, so it's monetized there. And also in South Australia, as I mentioned, for the reason I mentioned. Basically, Australia has also moved nationally with the national electricity market that is covering all the east part of the country to have primary frequency response mandatory for every single generator, but as well they're thinking about some inertia capabilities. But it's moving. In the UK, you have this National Grid Stability Pathfinder, but also that is creating new stability services. Some of them are coming live this year, the first ones, but it's a trend that should be seen in some other countries. So basically, yeah, that was. I took it short because I know we're just also running out of time. So if there's time for some questions, I'm happy to answer. Yeah.
Thank you, Michael. We're going to have to give the word to Mark for the following presentation, but thank you very much for this explanation of the technology, which is probably not intuitive for everybody, and this is why I wanted to have it here. Not everybody may be familiar with it, and interesting examples also outside of the European Union, also following up on Mark's presentation earlier with the UK grid example. And with that, I give the word back to Mark, and we're going to Mark's company this time. It's no longer a general presentation, but it's about your company. Mark, we do not hear you. I suggest you take over the controls because I do not have them.
Can Michael release the screen? Oh.
Oh, 1 second. Just hold on there, Mark. Hang on there. Yulong, you're back with us. Yulong, do you hear me? Just a question for Yulong, quickly. Perfect. So you can stay with us. Perfect, because we had it. Okay, excellent. Yulong, do you prefer, because I know that you signaled that you have a time constraint. Do you prefer to go before Mark, or would it be okay to go after, as planned? It must be okay to go after. I think Yulong can hear us. So Mark, go ahead, start. You got 10 minutes. Go ahead.
Hello, Mark Howitt again, this time being partisan, talking about my own company. Storelectric Limited, we're into large-scale, long-duration electricity storage using compressed air energy storage. We've got a number of new technologies as the world's most efficient and cost-effective storage at scale. So that, just to rattle through briefly, we started off wanting to, well, a colleague started wanting to work on hydropower and worked out that the only way that they could get the system to pay was to generate the electricity when it was wanted instead of when the tides wanted. And for that reason, he found existing compressed air energy storage in Huntorf and Macintosh in Germany and Alabama, but they have problems. They're far too inefficient, and they emit too much, so we had to look at ways of making it a lot more efficient, which is why I developed the test case, and a colleague developed the CCGT case. The first solution that we developed, the challenge with compressed air energy storage is not to do with the air. The way that it works is that when you have surplus or cheap electricity on the grid, you use it to compress air, which you store underground because that's the only place big enough. And when you when you need the electricity again, you let it out to blow a turbine and regenerate the electricity. The challenge is not doing the air. That's been done for decades. And in fact, about a third of the natural gas storage in Europe is in salt caverns, very similar salt caverns. The challenge is what you do with the heat. Traditional compressed air energy storage recognizes that you don't need the heat when it's being generated. As you compress air, about half of the energy of compression goes into heat and wastes the heat of compression. And our CCGT case technology is a traditional technology. It wastes the heat of compression. But at the same time, our particular configuration increases the efficiency of case storage from 50% up to 60% efficiency. In addition to which, traditional case can only be built new build using specialized equipment, specialized turbines that have been modified and certified separately. We can use off-the-shelf turbines and we can retrofit onto suitably located existing power stations. Our second technology actually addresses the question of heat. And instead of wasting the heat up a cooling tower, we put the heat into storage. And when we need the heat again, when we need to expand the air to generate the electricity, we put the heat back into the air during that process. And that actually increases the efficiency, grid-to-grid efficiency I talk about, not like batteries, which only talk about terminal to terminal. Big difference. Grid-to-grid efficiencies are up about 70% at scale. And these are for systems with a scale of 40 megawatts and upwards to multiple gigawatts, and for a duration of 4 hours and upwards. So it makes it vastly more profitable, and it's a similar cost to existing compressed air energy storage. We've also got hybrid compressed air energy storage. We've got 2 versions of hybrids. One is based on CCGT case, and the other is based on the thermal storage, compressed air energy storage, which is much more efficient. I'm rattling through this because we're short of time. I seem to have a different presentation slightly. There are various the technologies have been certified by numerous companies, such as Mitsubishi Hitachi Power Systems. So it's also been certified by Siemens and Costain, Arup, Fortum, you name them. And Mitsubishi Hitachi have not only validated the technologies, they say that they can build them from their existing equipment, their existing catalog, and can provide an EPC, which means that you can provide off-the-shelf infrastructure construction, and they're considering investment. We've got other technical validations from Costain, Fortum, Siemens, Mott MacDonald, and others. And they all say that it's standard off-the-shelf equipment, that it's highly efficient, and that it will work. The next sensible stage is to build an operating commercial system. We've even had the revenue streams validated. Unlike the presentation that we've just received from EDF, it doesn't look just at the energy costs in and out, but it also looks at the balancing services and ancillary services. But it only looks at about a quarter of the available ones, because these plants are more flexible than any other system on the entire grid. So they've evaluated these revenues in today's market in the United Kingdom, and there is lots of upside potential among all the other services that have not been evaluated. So these are commercially profitable in today's market and will get more so as the energy transition continues. Each location needs validating separately because each one has its own grid regulatory system and contractual system. And this is our team. A high-powered team, but most important with our team is that we also include all the engineering companies and multinationals that work with us in delivering this system, because they're very much on board and very much partners with us in doing so. Thank you very much.
Thank you so much, Mark. A very interesting presentation, and thank you especially for staying on time and even being ahead of time. Excellent job. We are now going to switch to Professor of the University of Birmingham, Yulong Ding, who is going to tell us about liquid air energy storage. Thank you very much, Yulong, for coming back to us.
Thank you very much. And can hear. Could you could I share the screen, or you share screen?
You have to share screen because I don't have any more the sharing option.
Okay, so I'm not sure which one I can click. So
there's a sharing pane.
A sharing pane. The sharing pane. Is this one? No, this is not. So I'm.
Must be right under the camera, the little camera icon.
Little camera icon. This one. Oh, I'm.
It should be right at the top.
Okay. We're not in it. We're not able to record.
I think it's loading.
Oh gosh, it's loading, is it? For some reason, I just okay. The PowerPoint. Let me just. I'm not able to record. I see there's a hiccup here. So. Can you see the slides? No.
Not yet. If it's easier, maybe you share it with me then, the organizer, and then I share the presentation I have.
Yeah, I think you have my presentation because it doesn't work in my, for some reasons. There are some security issues. I'm not really sure how it's done. So I think you have my presentation. If you could help share, that'd be great.
Yes, I'm doing it right away.
Apologies. So I was yes, that looks like the, yeah, that's the one. Yeah. So okay, great. If you could, I'm going to talk about liquid air storage or cryogenic energy storage. So before going forward, just probably some of you have heard the announcement of 85 million initiative to build 50 megawatts, 250 megawatts hours system this year, and the announcement was done last week. So that's exciting news for this technology moving forward to real commercial stage for competition. So if you calculate 85 million investment for 250 megawatt system and a megawatt hour system and the 50 megawatts power rating, you will see the numbers broadly in agreement with the data I'm going to show you. So if you move to the next slides, please. So the technology is very simple. Basically, is take air, clean first, compress, refrigerate to produce liquid air, store liquid air, and the compression heat is stored as heat store, and similar to compressed air storage, which Mark just talked about. When you need electricity, what you do, you pump liquid air to a higher pressure, because pumping consumes little energy or power, and hence it's a highly efficient process. And you use environmental air to heat up liquid air, because liquid air is minus 190 degrees C, and vaporization, and then expand in the turbine to produce electricity. And in the process, you will recover the cold, because minus 190 degrees C is very cold. So when you actually heat it up, you recover the cold. And the stored cold is roughly about minus 160 degrees C, which will be recycled back to the refrigeration loop. And hence, you have a high relative efficiency, which is roughly for standard known system about 60%. So basically, 1 kilowatts electricity in, and you have a 0.6 kilowatts electricity out. This is broadly what has been validated through the pre-commercialization plant. So next slide, please. Thank you. Yeah, next one. So the history is very simple. Basically, it was invented by my team 15 years ago, maybe 16 years, around 2004 and to 2005. And we did a sort of a 15 kilowatt system, 35 kilowatt system. Then around 2009, there was 350 kilowatts, 2.5 megawatt hours pilot plant, which has now been moved to our university campus. And you're welcome to come have a look. And then 5 megawatts, 15 megawatt hour system built around between 2015 and 2020, which is this year, and which is the finish of the commercial demonstration. And now they are building 50 megawatts, 250 megawatt hour system, which is I think the date there was wrong, because I predicted that it will be 2020, 2023. Actually, it will finish around 2022. So about 18 months lead time. And also the designing has been done on the 200 megawatts to a 1.2 gigawatts hour system. So that's for next 2 years. So next slides, please. So the operating regime can be for large-scale system. One click, please. And it can be for small system as well. And so large-scale system has been commercialized, and they're building that already. Small system has not been commercialized because that was done around steam time. It is for combined heating, cooling, and the power. And we have built a demo system around 2013 and 2014, and so we are building another containerized system, which hopefully you will hear some news, maybe sort of not next year, probably the year after. So it's a bit sort of a longer than planned, but I think it's suitable for something like hundreds kilowatts to sort of a few megawatts, up to about 5, maybe 50 megawatts, below 50 megawatts system. So that's for city scale, can be built anywhere in city or campus, and so on and so forth. Next slide, please. So some experimental results. So it's if you click one more click. So basically it can start quite quick, as can stop quite quick as well. So startup time, I think, is about sort of if you want one more click, is about 2.5 minutes. So from start, from the instruction. So that's actually, yeah, carry on. So if you carry on to that slide, please. Thank you. So you'll see that's actually response time. It's about 2.5 minutes. So basically, you have an instruction, which is about 0.25 minutes, and then you start sort of the turbine at 0.5 minutes, then reaches the full, it's about 2.5 minutes. Actual response time is less than 2.5 minutes. So so it's quite quick. So I mean, you can do secondary frequency regulation, and possibly the primary frequency regulation if it's running on the spin jam mode. We have tested the system. So the response time we found was about somewhere between 5 to 8 seconds. So still not quite to below 1 second, but I think we can realize between sort of 3 to 8 seconds. I'm quite happy to share the data if needed. So next slides, please. And this is what I refer to. This is a typical sort of frequency regulation sort of leads for this sort of applications. Next slides, please. So one of the sort of a key feature of the technology is that the use of waste heat. So if you actually have more waste heat, we can increase the efficiency a lot. This also opens an opportunity of a low capital cost system, basically, because the compressors cost a lot of money, and by using externally available waste heat from either renewables or industrial waste heat, actually they can reduce the cost, capex, and also increase efficiency as well. So that's what this slide tells us. So, and this is something which you can't really realize by any other technologies, batteries, or any other sort of technologies. So next slide, please. So people probably would want, what's the size of that? Actually, these are typical numbers of estimation. They are broadly correct. You know, the current sort of a pilot scale plant is very small, 600 square meters, and the pre-commercialized plant is about 1,000 square meters, and 20 megawatts, 80 megawatts hour system is about 1,600 square meters, and the gigawatts hour system will be sort of 16,000 square meters. They're pretty small. So next slides, please. And the cost. So, and this table shows the cost. So the left column is the scale, which is a power recovery units, which is how much power you want. So for example, 10 megawatts, 50 megawatts, and 200 megawatts, and the liquefaction plant unit and the tank size for the cold storage. And then on the right-hand side, you have a first of kind and tenth of its kind, and the first column is above the cost of if you look at the 34 millions, that's US dollar, and 92 million US dollar and 220 US dollar for respects systems of those. And for tens of its kind is a lot smaller. So basically, you can see the cost. So these costs actually broadly agree with what we have achieved. The pilot scale plant, the pre-commercial plant, and also the 85 million investment, which was just announced last week. So actually, it's cheaper than this shown in this table. So next slides, please. And this one actually is not very updated. I think the lithium-ion batteries has been dropped a bit, but still quite not too low. I think the probably is in line with the lead acid system. So next slides, please. I think this one probably is a people is a much clearer. So basically, if you look at the left-hand side, is a US dollar per kilowatts, and the right-hand side is about efficiency. So basically, if you look at sort of the first pilot plant, it's very expensive. It's about 10,000 pounds per kilowatts cost. That's dollar, and the 5 megawatts pre-commercial plant is about 3,000. And now what we are working on is a bigger system. Is about 16, about 1,700 per kilowatt. So broadly, they are in agreement. So I think that this sort of accuracy is quite encouraging. And I think if it's tens of the kind, I think that cost will be dropped by roughly about 30%. That's our prediction, and I'm sure that will be realized in my view. So next slides, please. So people would naturally compare the technologies. So we don't here. I just pick compressed air, which the market has demonstrated already. So and pumped hydro. So I think the main difference really is the geological constraints between those technologies. And the rest can be found in the next slides, please. So this the data in this table may not be very accurate, but I think they represents the order of magnitude. So happy to share these slides with the people and welcome to the debate on this. But I think it's different technology, and the efficiency can be high, and if it's small scale, it can be lower. So I think it's mainly for large scale applications, but if it's for small scale applications, combined heating, cooling, and power will be the best way forward for this technology. For standard non-systems, small scale is not workable in my view. So unless you use a half system, so you produce liquid air in in large scale in one side, you transport that and to a sites where the leads are. So that's the conclusion. Next slides, please. So basically the conclusions. So nuclear technology, the maturity is quite high. I think now is a commercial build stage, and it's easy to implement, and space requirement is quite compact, even compared with batteries. and geological locations, there are low limitation for that. The cost is competitive. So with that, thank you very much.
Thank you very much, Yulong. Interesting presentation. Congratulations on the grant. It's a very good 265 million investment. Very good job, and hopefully other entrepreneurs among today's presenters can also boast soon something comparable, because it's very hopeful for you. And yeah, hope that this is going to develop. This I suggest, since we're wildly over time, which I credit entirely to myself, because I'm really bad, horrifically bad with interrupting people in public. So I'm going to suggest that we end here. Thank you very much to ETIP SNET and to this initiative, and to all working group 2 participants who actually have driven the initiative. Thanks to Mark Howitt, the co-founder and CTO of Storelectric, to Enrique Morgades Prat, the head for market development of CIRCE, the Energy Institute, who told us about the storage technology markets, and who's also co-chair with ETIP SNET Working Group 2, to Etienne Sorin, EDF R&D Expert on Storage, to Silvia Bodoardo, the professor Politecnico di Torino, who talked about lithium-ion and other battery technologies, to Ramon Jarreau, R&D engineer at the Technological Institute of Energy, who told us about vehicle-to-grid and its role and energy flexibility and storage, to Michael Willemot, a CFO Business Development and Business Development Director at Oxtow Energy, who talked about inertia, to Yulong Ding, Professor at University of Birmingham. Thank you very much also to Luigi Lanuzza. Thank you, Silvia, for joining us. Yes, waving. And Luigi Lanuzza from ETIP Batteries, who shared the activities of ETIP Batteries and the cooperation with ETIP SNET, which is started. And thanks to our chair of Working Group 2 and the member of the governing board of ETIP SNET, Yves Schlumberger, for co-organizing. Thank you very much, everybody, for your time and investment.
Thank you, Anastasiya. Thank you, Anastasiya, for moderating.
Thank you. That's great.
And thanks to Zabala, of course, for the technical part, which is always challenging. And you guys handled it all right. Switching between.
Thank you, Anastasiya. It was great.
All the best. Thank you.
You have a great day, everybody. Good evening.
Bye-bye.
Bye-bye.
Thank you. Bye-bye. Bye-bye. Bye.